All right, the weakest type of intermolecular force, we've now looked at the ion-ion, and you know that that's strong because it's a charge-charge. And then the dipole-dipole, again, you have a partial charge existing in the molecule. When we say we have a polar molecule, we say it has a dipole moment, which means it's a measurable charge distribution when you put it in an electric field. But the last type of intermolecular force is the type that exists in nonpolar molecules. And there's different names for the same thing because so many people have tried to explain it. But London forces is a common term. Also dispersion forces, induced dipole type interactions, and van der Waals forces. These are all names that refer to the same thing, and that is the intermolecular force that exists in nonpolar condensed phases. Okay, so they exist in, and as it turns out, these types of forces, they exist in all nonpolar condensed phases. They also exist in polar molecules. Okay, they're present in both types. It's just that in the nonpolar, it's the only type of intermolecular force that exists. Okay, so it exists in both situations, but for the nonpolar, it's the only type that exists. And it's caused by what's referred to as induced dipoles. And an induced dipole is a dipole that comes and goes in a nonpolar molecules and free atoms. All right, and so the strength of this type of force depends on the polarizability of the individual atoms or molecules. What does that mean? Polarizability means the ability to become temporarily polarized. And so, for example, let's look at this example first. This is hydrogen, molecular hydrogen. Molecular hydrogen is a nonpolar molecule. There's no polarization, but we know that you can liquefy hydrogen if you can add enough pressure to get the molecules close enough to each other and cool it down enough. You'll get the molecules close enough to each other to where when they come near each other, the one molecule will induce a temporary dipole moment in the other. That means when this molecule here gets close to that molecule, this has got an electron cloud, this has an electron cloud, there's this temporary dispersion of the electron cloud because like charges repel. All right, so if these are both negatively charged, this is going to induce these electrons to be pushed over to this side of the molecule because like charges repel. Okay, so there's this repulsion going on, and once that sets up a temporary dipole moment, then you have a negative end and a positive end, which is going to then attract this electron cloud and induce a temporary dipole moment. And so once you have this unequal dispersion of the electron cloud, you can have a force. Okay, a force can exist, an attractive force can exist between the partially positive and the partially negative. Now the partials are going to be very, very small because you know, it's just a very weak dispersion of the electron cloud, but nevertheless, they do exist when these kinds of molecules can get close enough and move past one another slow enough to induce these dipole moments. And they come and they go and they come and they go. They can't be measured, but they must exist. And there's lots of evidence to support that they exist temporarily, which is what keeps these molecules attracted. Okay, and here's an example of just single atoms. They're not even molecules. So for example, this would be like an example of the noble gases here. There's no polarization. Again, if you can get them close enough and slow enough, then the electron cloud here is going to temporarily disperse this electron cloud because of the like charges repel. And then once that sets up a temporary dipole moment and there's a positive charge here that's going to attract the electrons this way and polarize, cause this to become polarized, and then you can set up an attractive force here. Okay, and so that's how it works. And so it says the strength depends on the polarizability, and you can see that the freezing points for these noble gases increase with mass. This is just going down the periodic table from the tiny to the big. And you can see, and the reason why, even though these are all just single atoms, this atom, xenon, has more electrons, so it's more polarizable. There's more slushing around or pushing around of the electrons that can occur. And so that's why the freezing points, again, also have to do with the strength of the attractive force. So the higher the freezing point, the stronger they are attracted to each other. Okay, and so that's why these would have a freezing point at -111, and this is -269, excuse me. That means you have to cool it down all the way to a much, much lower temperature to get it into a solid than this does, because this one's more polarizable. All right, so the London forces are a little bit abstract and a little bit maybe more difficult to understand, but nevertheless they are very, very important in all condensed phases, because they exist in all condensed phases. So the strength of the London forces, which is also called dispersion, induced dipole, and van der Waals forces, you'll see all those words, so you need to be familiar with all of them to describe. Dispersion, I think, is probably the next most common word used to describe this type of force. But the strength depends on also depends on the molar mass of the compound. Okay, so what you see with the London forces in the nonpolar compounds, that the more electrons you have, you know, the bigger the mass, the more electrons you have, the more of this type of force you're going to see existing. And so with these forces, the bigger the molecule, the stronger the London forces are going to be. You can tell by looking at the differences in these three molecules: pentane versus pentadecane versus octadecane. So that's, pentane would be 5 carbons, pentadecane would be 15 carbons, and octadecane would be 18 carbons in a hydrocarbon. And that's what's pictured here. None of them are polar. They're all nonpolar. The only difference is how many carbons they have, and therefore the extent of the molar mass. The shapes are the same. They're all just you know, long hydrocarbons. And this is the octadecane. It's actually a solid at room temperature and pressure. Okay, and you can see the pentadecane is kind of oily. That's an oil drip off of here. And the pentane is very similar to the hexane that you guys have experienced already in class. It's just a very volatile liquid. Okay, and so the strength also depends, in the case of the dispersion, on the shape of the molecule. All right, if you have a kind of a long molecule that can have lots of places for dispersion to occur, you're going to have more opportunities for that molecule to have forces existing, and so you would expect that it would have a stronger attractive force and therefore higher melting point and boiling point. If your molecule is kind of a circle or a ball, kind of rolled up kind of a deal, then less opportunity for overlap. You would expect the molecules to be weaker. So it depends on the shape also. So it depends on how big it is and the shape. And I like to have people think of Velcro when they think of these dispersion forces being additive. If you have like a little kid who's got their little teeny additive, that does not spell additive. That was weird. You think of a kid with a little baby shoe that has just like a little piece of Velcro on it, and a child's hand, which isn't very strong, can very easily pull the little pieces of Velcro. And Velcro's, you know, there's like a hook. It's just like a hook and a hook and a hook and a loop and a hook and a loop and a hook and a loop. That's how Velcro stays together. Imagine hook, loop, hook, loop. So if you're trying to use this analogy for dispersion forces, the more hooks and loops you have, the more opportunity for these little forces to add up. All right, so a little child's shoe would have less hooks and loops, and so it'd be easier to pull it off, you know, pull off that piece of Velcro to open the shoe. Or imagine, you know, you're wearing a whole Velcro suit and you're going to go throw yourself against the Velcro wall. Have you ever seen one of those? Okay, a person running, you know, towards the Velcro wall, all those hooks and loops that are on that suit can hold that person to the wall. Okay, so the bigger the molecule is, the more opportunity for these dispersion forces, the more polarizable it is, and that's why we can see, you know, nonpolar solids. All of these individual dispersive forces are adding up to actually allow the thing to be in a solid, even though the molecule itself isn't polar. And that's when you think of your petroleum products, all the way from asphalt up to the gases. It just depends on how big how massive those molecules are, how many opportunities they have for inducing dipole moments. So, so we see, like, for example, that the big nonpolar molecules can exist as solids, no problem, at room temperature and pressure, and even higher, due to even higher temperatures because of this additive force. So even though we say that the London forces are the weakest type, they are additive. So if you're just comparing, the same molecular weight, and you have an opportunity for a dipole-dipole, of course that's going to be stronger. But if you get a much, much bigger molecule, you're going to see that the dispersive forces add up, and they will have different physical properties than what you might expect.